Hi, everyone. A very happy Tuesday and welcome back to our ARM Tech Talk series. This is the place for the latest and greatest trends, technologies, and best practices from ARM and our ecosystem partners. And today we're talking about the smart city and analytics in real time at the edge. And we've got a host of panelists joining us today from ARM, Arcturus, and Renesas. It's going to be a really great tech talk today. I'm super excited about it, and I hope you are too. If you've been to one of these tech talks before, I've just got a couple of housekeeping items that you know about. If you haven't, particularly welcome to you. And I'm just going to go through those first before we get to the meat of today's topic, which is all about the smart city. So if we could head to the next slide, I'd love to tell you how we can get a bit more involved in the conversation today. So you can use any of the social media platforms with this hashtag and the OnArm hashtag to tell us more about what you're doing and how much you've enjoyed the talk today. All of our tech talks, 80 plus tech talks, are on demand. So do go and check those out on youtube.com/arm. And all of our upcoming talks are available on arm.com. So just head to arm.com/tech talks and you get all of the latest tech talk information right there, and you can register for any that take your fancy. If you want a little sneak peek of what's coming up, that's on the next slide with a nice table. Thank you. On November the 14th, we're going to be hearing about automotive voice AI solutions and Sophie from Sensory. And then we're going to be hearing from BlackBerry QNX the week after with some really interesting work they've been doing with their QNX Accelerate platform with ARM-based Graviton on Amazon EC2 and their offering. So super excited for that too. But of course, you've joined today to hear about the smart city. And I'd love to kick things off by handing over very shortly to Chakra, who's joining us from ARM. You can see a little biopic of him on the next slide, and we'll get him to turn his camera and mic on just in a second. If there's any questions you have at any point during today's presentation, please use the Zoom Q&A box, which is at the bottom in the menu bar, and we'll get to those at the end. So Chakra, you're up first. Please take it away with today's ARM Tech Talk, please, all about the smart city.
Thank you, Tobias. Good morning or good afternoon to you. I'm Chakra Akella. I'm the senior manager in the IoT line of business. I'm responsible for segment marketing as well as ecosystem partnerships. And I'm excited here to talk about smart cities. And let's jump right in. So let me first start off setting the scene that the entire landscape of smart cities is transforming, and there are many new use cases, many innovations which are helping the whole ecosystem be more safe. There are innovations around efficiency and driving richer experiences. So, for example, you have pedestrian safety that has been enhanced with the new applications. And you have new things like a traffic routing, smart buildings, which are improving the efficiencies. And there are richer use cases, such as parking lot, finding an empty parking lot spot. So all these innovations are driving benefits, and they're helping the whole ecosystem. Now, if you notice that most of these innovations have one common theme, that is, they are making the devices smarter. And that's the reason why AI and ML in smart cities is increasingly important. Now, what is ARM doing about it? The way we look at it, we are looking at it from a standpoint of making three major investments. The first one is having a strong IP portfolio to make sure that the products which are there are able to support all these machine learning capabilities. And then you have ecosystem and software. So this would include frameworks and making sure that the hardware is being able to capitalize on all the framework and all the open source work that is being done. And finally, developers are extremely important. So we are making sure that developer experience is enhanced. So in the subsequent slide, I will talk a little bit more into each of these areas. Now, if you look at ARM's IP portfolio, you will notice that we have on the left side of the chart, you have Cortex-M, which these are microcontrollers. These are for simple ML functions like vibration detection. And then as you move further ahead to the right, you have more computation capabilities. You have Ethos NPU, And then you also have Cortex-A microprocessors with the GPU, NPU, and so on. So the green bar on the right side is where you would see a lot of the content of this presentation, more higher end AI and ML on the edge kind of a use cases. One thing I want you to point out on this slide is that we are adding new capabilities and adding more ML processing with every generation. And these are enhancements such as better matrix multiplication, vector processing, and so on. So every subsequent generation, you will see significant improvement in performance as well as energy efficiency. Now, moving ahead, if this is another way of looking at it, so what you're seeing here is on the x-axis, you have vibration, voice, and vision. These are the popular categories of ML and AI. And on the y-axis, you see different kinds of IP or the processing capability. So starting off with vibration, most of it is lower end relatively, and you have some Cortex-A being used. And voice and language, now you're pushing the performance envelope. And finally, if you go to vision, that's where you have a lot of these applications like depth estimation, speaker detection, and all of them which need more processing capability. That's where you can use an NPU. That's where you might use a GPU or Cortex-A based NPU. Now, I want you to point out that if you are talking about smart cities, you are operating in this space. Moving ahead, now, these are examples of what are the different investments that we are doing in terms of frameworks, standards, and all the tools that are available for the ecosystem. So starting off, if you look on the top, we are engaged with TensorFlow, and then we are also trying to make sure that additional frameworks are supported. And then we are supporting open source standards like TOSA, and this converts operators to work on TensorFlow. And we have Model Zoo. If you're a new user, you just want to tinker, find out, then you have a few code examples. And these code examples are optimized for the underlying hardware. Same with TVM compilers. The compilers are able to use of the underlying hardware again. And same with the low-level machine learning functions through our libraries. And the ARM compute library supports both Cortex-A and the Mali GPU. Now, I would like to close off with mentioning about the ARM partner catalog, because when we talk about ecosystem, one company cannot do everything. So we need all our partners to come together. So this is a great resource if you're trying to build something on ARM. And you'll find that our next speaker from Arcturus, Jonathan, they will also be listed on this partner catalog. This is very useful resource for matchmaking and finding the right resource to build your next project. Okay. With that, I would hand it over to Jonathan.
All right, thanks, Chakra. My name is Jonathan Ring, and I am the lead data scientist here at Arcturus. Now, we often hear about the concept of the smart cities and the smart applications, but what I want to actually talk to you about today is what drives these smart city analytics, and eventually how they can be optimized for the edge. So this is just a brief overview of some of the analytics that Arcturus specializes in. They range from pedestrian safety and security, where you might just want to monitor high traffic areas, to something like retail and advertising, where you're monitoring more for the interactions and the workflow of those areas. And what you'll be able to do is extract certain demographics that might be useful for other analytics. But as I mentioned, what I want to focus on is what actually drives them and what makes them possible. So the answer to that is tracking. With every tracker, you're going to need your object detector to just be able to determine what objects you actually want to track in the frame. But tracking itself is the assignment of a unique ID to those objects, and then being able to maintain that unique ID or reassignment throughout the rest of the video. Now, the importance of this is that it is basically the foundation for all of the analytics that I previously mentioned. So if you think of a simple analytic such as loitering, where you're just trying to determine how long an object is in the frame for, if you can't maintain a unique ID, you're just going to be getting a lot of false negatives. You're never going to raise that loitering alarm. Now, if you think of a more advanced analytic, such as abandoned package, where what you want to do is create an association between a person and a package, if you can't maintain an ID here, and you keep getting ID switches, it's going to keep raising alarms that that package has been stolen, at which point you're just going to get a lot of false positives. So at this point, we can kind of start to see how poor tracking is just going to lead to poor analytics. Now, before jumping into things, I just want to briefly touch upon how different tracking algorithms or configurations might be needed depending on the system or the analytic requirements. So whether that be your frame rate or your available resources, you might need to pick and choose what your tracking configuration looks like. So if you start on the left here, a simple analytic such as intrusion, you'll most likely be able to get away with a simple motion tracking algorithm. Whereas when you start to work your way upwards in complexity and deal with analytics such as watch lists, you're going to need to start adding appearance tracking, long-term re-identification, and multi-camera tracking. So what this starts to do is beg the question, how do I know if I have the right configuration? Is what I've designed or what I've selected overkill? Can I drop down to a simpler solution? But how do I evaluate what I'm working with? And the answer for that is the MOT evaluation tool. So what this does is it allows users to submit tracking output that has been run on a varying set of videos. And what it does is allows you to receive useful metrics as to how well it's performed. So some of these metrics include the MOTA, which is your multiple object tracking accuracy, your IDF1 score, or your HOTA, which is your higher order tracking accuracy. And all these metrics evaluate slightly different things. So your MOTA is going to emphasize more on your detection accuracy, whereas your IDF1 score is going to emphasize more on your association accuracy. So not only is this a great way to evaluate your tracker and see where you might need to make improvements, but it's also a great way to select a tracker if you're not developing one yourself, and see what might be the best tracker for your analytic. Now, what this image is showing is Arcturus's in-house BrinkTrack tracking algorithm and how we were actually able to achieve #1 across the board for MOT16, MOT17, and MOT20. And this is just a quick video from the MOT20 dataset showing how complex some of these videos can get and how useful this tool is, and how you wouldn't really be able to evaluate your algorithms just by looking at it visually. Okay, so to dive into the tracking algorithm and how we actually achieved such high results, and some of the possible methodologies that we used, but also some of the limitations of each. And then I'm going to try and take all those pieces and create an optimal solution that is able to run at the edge. So looking at some of the building blocks of tracking, as I mentioned, you're always going to start with your detector to determine what objects you're tracking and where they are in the frame. Then what you're going to want to do is make predictions given your previous tracks and their states and the previous detections. And then take those detections and the predictions and run an assignment algorithm. From there, you pretty much just need to draw a conclusion based off of the output from your assignment and determine, am I going to create a new track? Am I going to delete a track? Or am I going to simply update a track with the same ID? Now, when we think about tracking, it can typically be broken down into two main models, which are motion and appearance model tracking. And the main difference between the two is that the appearance model tracking is going to utilize a feature extraction network, which is going to tag an embedding vector to each object. And what this aims to do is help with the association, because you now have a descriptor of the object versus pure motion. That being said, so motion just relies solely on the predictions based on the previous states of the objects, and it's usually working with a constant velocity model. So starting with the motion model, just looking at some of the strengths and weaknesses. The main strength is that it has pretty much maximized the performance versus accuracy trade-off. So a lot of the top MOT trackers that you'll see are actually based off of this motion model. Now, the reason for this is that it can pretty much achieve the same accuracy, but at a much lower cost. And this at least holds true for the MOTA metric, but not necessarily the IDF1 metric. Another strength is that the computational time is fairly predictable. And the reason for this is that you're only using a single neural network. So it's not necessarily constant because the time will still vary depending on how many objects you have in the frame when you run that assignment algorithm, but the ranges are very minimal compared to introducing a second neural network. Also, if you've ever heard of the SORT algorithm, the simple online real-time tracking, it's very famous, and this is what a lot of the top trackers are based off of. And then they kind of add their own tweaks to it and optimizations. But the base for a lot of these trackers is just the SORT algorithm, which in its name, it's simple, it's easy to use, and just very lightweight. Now, looking at some of the weaknesses, I think the top weakness for motion tracking is the robustness to occlusions, because you are making predictions purely off of that constant velocity model. So if you think of a person walking from left to right, and they've walked behind a pillar, and they're fully occluded, and then they decide, hey, I want to turn and walk the other way, this motion model isn't going to be able to pick that up. The predictions are going to keep going in the direction that the person was originally walking. So it is very, very sensitive to occlusions. Another weakness is limited smart city applications that you can run. So you're not going to have long-term re-identification. You're not going to be able to track somebody that walks out of the frame and comes back in a day later. It's just simply not possible. Another weakness is camera motion sensitivity. So whether you have a shaky camera or a camera that might be on top of a moving bus or a moving car, if you're making your predictions and the camera shakes and all of a sudden that person becomes located in a different position, the motion model is going to do an incorrect association. And finally, we have a little bit of a frame rate dependency. So whether you're working with an inconsistent frame rate in your real-time system, or if you have a low frame rate, what this is going to do is create a larger distance that the object has traveled from the last time it was seen from its previous state. At this point, the predictions from your motion model are going to start to become a little less accurate, and this is then going to lead to incorrect association. So jumping over to the appearance model tracking strengths. If you recall, the appearance model tracking is now using an embedding vector, which is to try and help with that track association. So if you think back to my previous example of the person walking behind the pillar and then deciding to go the opposite direction, where the motion model will fail, the appearance model is going to help try and pick this up, because you can use those descriptors of that object to try and reassign this and say, hey, this is the same object. So as a result, you have your increased robustness to occlusions and an increased association accuracy. And as a result of that association accuracy increase, you're going to have a higher IDF1 score. You will see a slight increase in the MOTA score due to the reduced number of ID switches. And also, you would hope to see the reduced number of false negatives and false positives. Now, a big selling feature for the appearance model tracking is the advanced analytics. So now you're able to run long-term re-identification. You can run the multi-camera tracking. And that's kind of what I've laid out here in this multi-camera tracking example, we can see the guy in red successfully go from camera 1 to camera 2 and maintain the same ID of 45. Now, the reason I've laid out this example is to be able to just do a quick embedding analysis on it. So what this graph illustrates is how accurate some of these descriptors can be, and how using something as simple as a Euclidean distant metric is going to be able to differentiate object A from object B. So what this is doing is comparing the embeddings of the guy in red to the stored embeddings of the other objects that are in the database, which is the green and the white shirt. And what it's just trying to show is how it can create very similar embeddings with a small distance and allowing us to confirm that it's the same object. Now, that being said, it still has its limitations. So where we begin to run into difficulties is when there's some confusion between these objects. So even though the appearance model tracking has its increased association accuracy, it still has its sensitivities. So this here in the top left corner, you can see how the girl in the white shirt has gone from a standing position to a crouched position. And something as simple as that has caused her embedding distances to spike. Here, where we can see the embedding distances becoming more similar between different objects, is because we're starting to see partial occlusions. We're starting to see overlapping of the bounding boxes. So these embedding distances are getting much closer. Now, there are a couple of solutions to handle such issues, but I'm going to touch upon that a little bit later in this presentation. Okay, so now for the appearance model tracking weaknesses. The main weakness is that it's computationally expensive. So as I said, it's going to require a second neural network, or it's going to require a joint detection embedding network, a JDE. But either way, it's going to cost you. So when you start to run this second neural network, what you'll typically see is a performance bottleneck, which you can see in the graph here on the right, because you're going to have to run this network X number of times for X number of objects that are in that frame. So you can kind of see how we go from 1 object to 10 objects to 100 objects, how that starts to add up. And the image just here on the left is actually taken from the MOT20 data set, where it has an average density of 178 people per frame. But we've actually seen 200 plus people in the frame. And again, you can infer the impact this is going to have on your tracking algorithm, but also on your overall system. Finally is the domain sensitivities. So the robustness to low light, crowded scenes, how many partial occlusions are there? What objects are you trying to track? Are they similar looking objects? So I like to think of a use case of tracking outside a sports arena. People will most likely be wearing the same sports jersey, same color, maybe different numbers, but it's going to be very difficult to differentiate between object A and object B. And if you can think back to the embedding analysis graph I just showed, the descriptors of people wearing the same jerseys is going to get confusing. The lines are going to start to overlap, and you're pretty much not adding any benefit using your appearance model tracking at this point. So a quick summary of what I just talked about and how the main thing to focus on here is the performance versus accuracy trade-off. So just looking at this graph and our brink track solution, we chose a network and an algorithm to optimize our accuracy. But if we wanted to reach a higher frame rate, we could do techniques such as using a more lightweight model. But that being said, if you're going to reduce or use a more lightweight model, it's going to be at the cost of dropping your accuracy. One thing to note from this graph, though, is that we do have a very high IDF1 score, which is represented from the radius of our circle. And that's just showing that we still have a very, very strong data association accuracy. So what can we do to improve our algorithm and try and reach those high results and get #1 on the charts? One tracking improvement, which is very easy to do, is called noise scale adaptiveness. So the goal of this is to actually utilize some of the lower confidence bounding boxes. So if you can think back to the sort algorithm that I had mentioned, what it typically does is act as a low pass filter and you're discarding the detections below a certain confidence threshold. At this point, you're losing a lot of data as you have that hard threshold. So what we want to do here is actually retain that data and use it in a meaningful way. So based off of this formula, you're able to inject the detection confidence into the noise covariance to create an adaptive noise covariance. So what this will do is for the greater confidence bounding boxes, you'll have a smaller noise covariance, and that detection will have a higher weight in the state update. And as a result, this is going to improve the overall accuracy of that updated state. Another easy to implement technique is simply modifying the state vector of your Kalman filter, which is used for predictions. So you can swap out the predictions. Instead of predicting the aspect ratio, what you can do is actually predict the width and the height directly of the bounding box. So what we've seen here is an actual improvement in the localization of the bounding box. So you can kind of see in the image here that we're no longer cutting off the toes or possibly cutting off ligaments. And this will increase our predictions. But you can also think back to the appearance tracking, where it will hopefully increase how accurate your embedding descriptors are, because you're not cutting off valuable information. Another improvement is for the camera motion. So I discussed how that's going to affect your motion model and how that is going to be a pretty big weakness. So what we can simply do here is just try and compensate for that camera motion. And what the goal is to derive a 2D transformation matrix that you can just apply and correct your predictions with. Now, there's a couple methods that you can use here, which also have the performance versus trade-off accuracy. And we just chose to go with the ORB, the oriented fast and rotated brief feature matching, purely because of its high accuracy. So if you can recall the previous embedding analysis I did, and where we started to see some of the effects of those partial occlusions and the poor detections and initial detections and localizations, and how those embeddings became closer in distance. What we have here is called the body part-based reidentification, and the goal of this is trying to increase the robustness of those partial occlusions. So what it actually does is it segments the body parts to only use the visible body parts for the embedding comparison. So say we have this blue bounding box here. It's a query image. This is going to act as the object that you're trying to re-identify in your current frame. The first step is going to be to segment the body parts. And then we're going to start to do the comparisons against whatever other data you have in your database. So here we call it the gallery. So we can see that in the first gallery image, the legs and the feet aren't visible. So we don't use that in our embedding comparison. And we end up with a score of 0.57. So if we didn't segment this and we used the whole bounding box area, we would get a much higher score than 0.57 and most likely wouldn't be able to reassign this person as that ID. Now moving on to another, no occlusions, but another image in the gallery, we can see that it achieved a score of 0.61, which is nearly the same score as the occluded one. And that's exactly what the goal here is to eliminate the noise and generate similar embeddings for similar objects, regardless of what the occlusions may be. And finally, we have generative AI pose estimation. So this is trying to help with your long-term re-ID or your multi-camera tracking. So again, if you think back to the embedding analysis where the girl in white was standing, then she went to a crouched position, the effect that kind of had on the embedding and what was describing her essentially. And this is just trying to target that weakness. So this can be used for online and trying to expand that gallery so that when you do that embedding comparison, it's against data that is more closely related to what you're using as the comparison. But you can also use it for offline model training. So you can increase your data sets with synthetic data set augmentation and try and help with generalizing your feature extraction networks. Okay, so we have all these pieces to construct our pipeline and a tracking system that works for your particular use case. But how do we actually apply this to the edge? And how do we optimize that pipeline to squeeze the most out of your hardware, but also out of your software, GPU acceleration within the pre and the post processing? So depending on whether this pre and post processing is built into your model graph, it's most likely not going to take place on the NPU. At which point we have actually seen the pre and post processing take longer than a single forward pass of that network. So this is where you have options to accelerate, including Mali GPUs, or in some cases NPUs, such as the Renesas DRP AI, which Brian is going to talk to you about in a bit. But the main point here is that it's important to assess what your bottleneck is and what acceleration is going to help. So we make use of hardware acceleration wherever we can. So on the CPU side, we make use of the ARM Neon, have seen a performance uplift of roughly 3 times. And on the NPU side, we typically see a performance uplift of 10 to 30 times. That's going to be very dependent on your model. And this can be seen with NPUs such as ARM's Ethos or the Renesas DRP AI. Now, I think with that being said, this is probably a great place to hand it over to Brian from Renesas to talk about their Edge AI hardware and some of the performance optimizations that they're able to achieve.
Thanks, Jonathan. Appreciate that. My name is Brian Whitson. I am the Principal Business Development Manager for Renesas, and I focus on the ARM processors devices that we've created called the RZ product line. So today what I want to do is I want to kind of discuss some of the AI trends and specifically how they relate to AI at the edge and edge points. Also some of the challenges of implementing embedded AI systems. And then finally, we'll present a few of the Renesas scalable solutions for real-world applications like Jonathan mentioned that are used in smart city applications. Well, you hear a lot about AI, especially in the news right now. You hear both good and bad. Much of that's related to cloud applications. And in reality, what we see is actually there's a huge growth of AI at the edge and endpoints using both ML and neural networks. While the AI training and learning is still typically done in the cloud, AI applications performing inference with real-time data is really becoming a vital first step before moving that data into the cloud, and sometimes actually eliminating the need for that cloud interaction at all. Oops, sorry, I went one too far, sorry. AI applications for the edge and endpoint are really expanding into everyday products from real-time well in the smart city app topics mentioned by Jonathan earlier. Sorry, I don't know why it's jumping 2 instead of 1. Here we go. So vision AI is really, as Jonathan mentioned, is transforming from simple object detection to much more advanced human behavior and vehicle management applications. So this is really driving the demand for more diverse AI models and higher performance from the processors. Many of today's new devices are incorporated neural network accelerators that are self-developed or provided by companies like ARM. So some of the 3 big challenges that we see in embedded AI systems are heat generated by power consumption, excuse me, AI development skills, and scalability. Sorry. I don't know what we're having a delay in the slides here. And the increased heat being from the demand from explosive growth for required computation. And the skills that we're finding are difficult to secure because of the new edge and AI endpoint products. And then companies trying to make them. AI is really kind of a new technology for them. So they're finding it difficult to find the right employees to fill those gaps that they need. And then, of course, scaling across both multiple products really requires designing for an efficient platform and key processing devices and software that you can reuse from one product to the next. So as far as heat and power consumption, vision AI requirements have really drastically increased in the past 20 years, leading to an explosive increase in the computational demands from AI devices, just as been mentioned earlier. You can see on this slide that AI model requirements have gone from basically from millions of Mac operations to tens of billions of Mac operations for today's models. And we actually, today we actually measure AI performance in TOPS versus millions of operations. We're actually talking about trillions of operations per second. And then again, frame rates and vision resolution demands have increased. This has led to an increased computational requirement, which demands more powerful processors and therefore increased power consumption and generated heat. And when we look at the idea of development skills, well, AI is being added to more and more edge and endpoint products. So this is increasing the need for employees skilled in AI development and deployment. The AI model creation skill set is really different from traditional embedded software design. So they have to think of a lot of different things. They have to think of like, how do I create and train the model? What model should I use? What data set is best to start with? What framework should I use? And in a lot of cases, even where do I start? A lot of the customers that I've called on, I've found that many companies are new to AI and really just don't understand what it is that they need to do, but they know that they will need to use it. It is the future. The other thing to consider is scalability. It makes sense to reuse as much of the AI software and hardware development as possible. Many of the AI-focused semiconductor devices are designed for very specific uses. They may work very well in their intended application, but they don't always scale very well to multiple applications or products. So that's another thing to definitely consider in product development. So I do want to introduce you to the Renesas family of products for AI. So we've developed this family we call the RZ family of processors. The RZ family is based on the ARM Cortex processing cores, with the RZ-A being the RTOS general purpose device. The RZ-G is our general purpose Linux flavored device. And then the device I want to talk about mostly today is really RZ-V, which is focused on our vision AI. And it is a good solution to the issues of heat, lack of skill set, and it provides a wide range of scalability across the platform. So the RZ family of devices, it was really designed for edge and endpoint embedded vision applications. So really specifically for the market that we're talking about today. So the RZ-V family is powered by the ARM Cortex A53s, A55s, M33s, R8s, and we even use the ARM ISP core. And that each core varies depending on the family and the device we're actually looking at. They're designed to be scalable across the whole family. So from software and hardware, a lot of the resources are reusable. And the RZ-V uses what we call the DRP AI. So this is a Renesas developed neural network accelerator with performances up to 80 TOPS and power efficiencies up to 10 TOPS per watt. And the latest DRP AI, we call it DRP AI 3, supports AI sparse models for even more improved performance and power efficiency. To give you a general idea of what our DRP AI actually looks like, so essentially it's a tightly coupled, dynamically reconfigurable processor, which we call DRP, and then AI MAC, which is a multiply accumulate. So the DRP AI neural network accelerator really improves the power efficiency inference and pre and post video processing. And the way that it does this is basically the DRP can offload CPU for the performance of pre and post video processing, such as color filtering, color correction, gamma correction, noise reduction, all those wonderful things that you do in video before you form AI on it. And then when you're talking about the actual neural network model, where convolution layers are basically linear operations that involve multiplication of weights to create this feature map that we use. That's done very well in the AI MAC because it's basically all multiply accumulate functions. And then when you look at things like the pooling layers, which are used to downsample the feature map to reduce the sensitivity of changes in the video, that's done very well in our DRP. Because as the pooling layers are used in the deeper portions of the model, different feature sets can be detected. And those functions used throughout the pooling layers from the beginning to the end change, and therefore they fit very well with the flexibility of the DRP because it is dynamically reprogrammable. And almost instant reloading when we change from one arithmetic function to another. So that's where we see a lot of power efficiencies come from in the DRP. This next slide, there we go, is basically just an example of our DRP running against a traditional GPU type application. And in the picture, you can kind of see this is a test board, but our DRP AI device on the left-hand side does not have a heatsink or a fan, where the GPU on the right side does have both. And the performance of this device compared to a 6-core GPU, we're performing the inferencing in less than half the time, and our power consumption is drastically reduced. So therefore, hopefully eliminating at least the need for active cooling. In some cases, you may still need a heatsink, but for a lot of cases, you will be able to get away without having any kind of active cooling measures. So therefore, fighting the power consumption heat issues. So for the development skills portion of the problem, we've actually developed solutions to reduce the need for specialized AI skill sets, ranging from everything from our purchase of Reality AI a couple years ago, which helps with real-time analysis of machines and audio, onto our MCUs, which we have a wide range of those as well, to providing pre-trained models for the RZV Vision AI devices, which are free of charge and have really no prior knowledge required to get these things up and running. And just to give you an idea of some of those devices that are available, so we've actually teamed up with some of our third parties and created actual applications where most of our competing manufacturers actually they may provide the SDK or some kind of development environment and a few model examples. We've actually taken this a step further, and we provide a complete solution with pre-trained models for many different applications. And I've kind of highlighted some of those in red that we see tend to use in smart city applications like Arcturus described. And then the other thing that we've done is we have a large ecosystem of vendors that support AI model development, model compression, AI applications of all kinds. And then they also have a lot of hardware and software vendors. The hardware guys providing SOMs and SBCs for almost all of our devices. So this helps reduce the need to have a complete internal AI skill set at all levels of the product development. So you don't have to hire people for every single part of this new AI world that we're living in. And from a scalability standpoint, this is just a quick show of some of the devices on the RZV product line. But you can see that we scale basically from 0.4 tops, which is a good entry-level device for doing object detection and facial recognition, things like that, all the way up to the higher-end RZV2X, which is a device coming out toward the end of this year that's going to have quad A55, Cortex A55 cores. We've actually implemented 2 of the Cortex R8 cores for motor control applications, and then a full set of peripherals to go along with that. But basically, you can see from this slide that we have scalability from entry-level, low-end performance devices all the way up to the higher-end 80 top realm of product. So from just a takeaway from these slides is kind of the fact that Renesas, the RZV printer MPU product line, provides full flexibility, power efficiency, and real-time vision AI applications is really its target focus. We have scalable solutions to solve the entire embedded AI challenges, easy to use tools, third-party solutions that are Renesas ready, that have been tested and qualified by Renesas, And then we have Renesas AI solutions that contribute to the innovation, creative edge and endpoint product lines. That's all on my side. I send it back to you, Chakra.
Actually, it's back to me. Thank you, Brian.
Yes.
No problem. No problem. Yeah, that's just thank you. That's really, really great presentation and super really excited to see from Arm, Renesas, and Arcturus. Jonathan, Chakra, get your and Brian, keep your cameras and mics on because we're going to have some Q&A time now. So, audience, if you've got any questions, please use the Zoom Q&A box to ask them, and I'll get to ask them during today's presentation. So let's just get everyone sorted. So I'm just going to quickly go through a couple of questions. I've got a couple, and then we've had a couple come in already. So I'm just going to go around one each of you. So Chakra first. Actually, before I get to Chakra, I loved how you mentioned the Arm Partner Catalog. You know, it's one of the key benefits of the Arm Partner Program, having your page in the B2B marketplace that is the Arm Partner Catalog. It's a very successful, very popular part of arm.com. It's great to see Renesas and Arcturus having a page in there. So do go and check it out if you're interested in building an ARM-based product. Do go and check it out. And also, if you're interested in joining the Arm Partner Program, just head to arm.com/partners to do so if you've built an ARM-based product. So Chakra, on your side, I know you mentioned a lot about these AI-based use cases for the smart cities. Are you seeing these use cases getting traction in the real world, though?
Yeah, I mean, there is a lot of innovation. So there are some applications which definitely have more traction than others. And there are a few applications like a smart parking, which are seeing a lot of traction, and others are still being tested. So as the market matures, we expect to see more traction in these use cases.
Brilliant. Thank you for that, Chakra. And Jonathan, I'd like to flick to you on your side. You know, you mentioned I'd love to go into a bit more about what you mentioned around MOTA and IDF1 in your section of the presentation. I'd love to go into a bit more into that on your side, Jonathan. You know, do you typically focus on the MOTA or IDF1 when constructing a tracking algorithm for your analytics?
Yeah, that's a good question. The ultimate answer is it depends. It depends on what you're looking for, right? Ideally, you want to be high in both your MOTA and your IDF1, as you want your high detection accuracy and your association accuracy, but it can also be very dependent on your domain. So if you have that crowded scene of 200 people plus in the frame, you might want to focus on having a higher MOTA score to get those clear and concise detections, which as a result is going to help with your tracking.
Brilliant. Thank you so much for that, Jonathan. And I'll go over to you, Brian, on your side. You know, you talked about the pre-trained application side. How can people try the pre-trained applications?
Yeah, so the pre-trained applications are something Renesas actually developed, in some ways using third parties for the application development. But basically, all those applications are done with open source concepts. So everything is available on the web, both source code for the applications and the pre-trained models are available for downloading. You can run it on your own hardware, or you can actually get one of the Renesas EVKs or eval boards and easily run it on that. And then we have a bunch of apps engineers that can help you get up and running as well.
Awesome. That's great to hear around the open source side here. Do get in touch with the Renesas folks if you're interested in that, and do try that out. And we've had a couple of questions come in, and I think they are targeted towards yourself, Jonathan, on your side from Arcturus. I'll go with and if you see a question that you like, by the way, as they come in, that you want answered first, just hit the little thumbs up button. I always get to the most upvotes first. So I'd had one come in here from Taha. Apologies for mispronouncing that. I'm not getting that quite correct. Does the lower thresholding create a surge in false positives? And if so, how does your noise covariance method handle that?
Yeah, so that is a good question. You can see an increase in the false positives depending on how low you actually lower that confidence threshold. But what the goal is here is to actually find a sweet spot with that confidence threshold to be able to maximize the true positives. So as I kind of previously stated, the noise covariance is going to be greater for your lower confidence bounding boxes, which is going to lower the weight in that state update. So hopefully with the adaptive noise covariance within the Kalman filter, that's actually going to discard those garbage detections still. But like I said, it's still very sensitive as to what you set your lower bounds for with that confidence threshold. But it's just, again, trying to find that sweet spot.
Awesome. Thank you for that. I hope that answers your question, and do follow up if you've got any further questions off the back of that. And then we've had another question come in around the model and the hardware that was used for tracking in that video you showed as well, Jonathan. Do you mind just going into that a bit more?
Yeah, for sure. So the model was an in-house model. Arcturus actually has a lot of expertise in training custom models, whether it's unique for certain domains or whether you want to track certain objects. So for that MOT data set specifically, we trained a custom YOLO v5 model. It was an extra large model. So again, we wanted to get the most accuracy here. We weren't really worried about performance. As far as the hardware it was run on, it wasn't run on an embedded device. However, we do have support for the YOLO v5 models to run on, like I mentioned, the NPUs for that acceleration. But if you are trying to look for something that is more performant with respect to frame rate, what we do in-house is to train more of a lightweight model. So maybe YOLO v5, nano, small, medium, and still have it be custom, but that way you can run it at the edge.
Brilliant. Thanks so much, Jonathan. And I think we're getting close to time. So what I'd love to do is for each of the presenters quickly, and I'll start with yourself, Chakra, on your side. Do you have any final words or anything you'd like to finally say as we start to wrap up today? Any final calls that you'd like to give to the audience today on your side? Firstly, Chakra.
Yeah, I would say if there are any further questions, please reach out to us. We are continuing to innovate and continuing to work on these challenges. And please join the ARM Partner Program. That would be my call to action. So yeah, that's pretty much it.
Thank you, Chakra. Yes, please do. Absolutely. We'd love to hear from you. And Brian, next on your side, any final words you'd like to share with the audience today?
I think I'd just like to say, I mean, the world of embedded AI is just growing tremendously. We're seeing it being added to almost every device out there. And a lot of customers are even looking at it, knowing that they're going to have to involve it in some way in their product line. But it's coming, and it's going to be great. We're going to see all kind of amazing things come out of it. So, look forward to it.
Absolutely. It's very exciting. And Jonathan, on your side, finally, any final words on your side?
Yeah, it is very exciting. We're excited. We're always developing new things, leading edge research. So we're excited to continue to push forward. And if you guys have any questions, don't hesitate to reach out. You can just email me directly. So it was a pleasure.
Thank you. Yes, do reach out to any of the presenters involved. We're sure you've got more questions on the back of this and be interested in following up with their solutions and their products. So please do follow up with them. All that remains to say is thank you so much for joining yet another one of our ARM Tech Talks. These are on the same time every week, 4 p.m. UK, 8 a.m. Pacific. So do join us next week for another ARM Tech Talk where we'll be hearing about voice AI solutions in automotive and the work we're doing there with Sensory and the work that Sensory is doing there and the work on Sophie that they're doing. And that's all about the latest trends, technologies, and best practices. That is what the ARM Tech Talk series is all about. So Chakra, Brian, Jonathan, thank you so much again for a great presentation. Audience, thank you so much for your great questions and for attending today. And we look forward to seeing you again at the same time next week. Thank you so much.